Welcome one and all, Coach Jay's podcast, Chapter 7, AP Stats. How are you? Hope the team's doing well as we get started on what might be the first full week of the school year. Hey, welcome. Come with some questions today as we get started. We're going to look at FRQs today. We're going to look at multiple choice questions. The goal today is to help you however I can. So if you are watching live, please make sure to throw out those questions. We'll go through those questions together. I see that there's a lot of viewers right now, 0. I'm hoping that's going to change a little bit. Maybe it hasn't updated yet. And I'm just excited. I'm excited to get it rolling. Excited for the Sunday afternoon. Excited about tomorrow's test. Good opportunity. Hey, tomorrow I'm going to be there at 7:15, even 7. If you want to come in a little earlier and get some help on some of those questions that are there. A lot of you have already finished that homework. If you haven't, chapter 7.3, make sure you finish that homework. And if you've already finished, make sure notes are there. Make sure the FRQs are done. And get it and go from there. Hey, before we get started, make sure I did notice on the note sheet that there were a few of the FRQs that I did not provide the answers to. That is my fault on that. However, if you simply wanted to find the answers, go to the bottom of chapter 7 page for the FRQs. Make sure you get that done, and turn that in, okay? So just make sure that you have that due by tomorrow. All right, so with that being said, I'm going to get started on an FRQ question. And the whole idea of this is for you to be helped by this. So if you could, just throw out those questions that are there, and we'll try to go through it together. A couple things to kind of mention to you first before we begin. I'm going to actually pull this over. Okay. A couple things to mention to you before we begin. Remember, the comparison sheet is very, very important, and I'll kind of throw this up here. The comparison sheet that we're going to go through is very important for you in terms of the test. So be sure that you know this, know when it's applied, know when the 10% condition occurs. Those are things that you're going to really need to know, and a lot of application on both the FRQs and the multiple choice will help you with that. So just again, a heads up on that. Make sure you get that done and understand what's going on there. Okay, we'll rock and roll. Hey, as we begin, we're going to start on the FRQ. I would also take a good hard look at which formulas are on the formula sheet, which ones you'll need to know, especially the ones you'll need to apply. So if you, for some reason, have some questions on that, you can always email me or text me or even ask it in this podcast, but that's going to be important. Out of all of the ones you see here, which ones do they give you and which ones do you need to know, okay? So just a heads up on that. All right, so with that being said, I think I already gave you the 2 FRQs that are going to be good for the test. I think I told you the candy machine one, and the second one I told you was the train one. Those are 2 ones that are good. Those are good ones that I would look at and go through. This one right here, though, in 2007, number 3, this was off an AP exam, and really good one with our when we talk about sampling distributions. It's a good one here, good application, okay? All right, so let's talk about this first. It says, Big Town Fisheries recently stocked a new lake in a city park with 2,000 fish of various sizes. I kind of like to highlight that or circle it. That always helps me kind of know, all right, this probably is going to be our population. We'll check it out, but I'm probably going to be our population. The distribution of the lengths of these fishes is approximately normal. That's very important because it gives us a couple things. The distribution of the lengths of these fish is approximately normal. That means we're probably going to be talking about means, a sampling distribution with means. And since the population's approximately normal, that means my sampling distribution will be approximately normal as well. Okay, so just a heads up on that. You might want to state that if they ask for that, and we'll go from there. So with that being said, it says this. Big Town Fisheries claims that the mean length, there it is again, of the fish is 8 inches. So I would say that mu is 8 inches, meaning the mean of the population is going to be 8 inches. If this claim is true, so we're going to assuming it's true, which of the following would be more likely? So now we go into the questions, and this is where we analyze this together, okay? All right. Which would be more likely, meaning where would the probability be greater, okay? That's what we're looking for, all right? All right, so let's look at this. Okay, so as we look at each of these, we say, all right, a random sample of 15 fish having a mean of that is greater than 10 inches, okay? So the first thing we want to do is kind of just set up something. First off, we know that in this example, that big N would be the normal distribution because the population distribution is normal. We're going to say that having a mean length, well, now we're going to have the mu of x bar, comma, my standard deviation of x bar, okay? That's what we're looking at. And we know the mean length is 8, so we're going to say n of 8, comma, and my standard deviation, we don't know this, okay? So we don't know that. So that's the first one. We'll come back to that. The second one says this, big N, okay? Because again, it too is normal distribution because it refers to the population. We have the mean of 8 still, and my standard deviation, I'm still not sure of, okay? So what they're asking is out of the first one and out of the second one, which would have a higher probability to have a length that is greater than 10? Well, really what they're asking for is which data would be more spread out. Would the data for the first one, which takes 15 fish, be more spread out, or the one with 50 fish? Well, to do this, what we can do is figure out an estimate of what the standard deviation would be. So if I was trying to find the question marks for both of these, I would say for the orange one or the first one, the standard deviation of x bar is the standard deviation over the square root of 15. Okay, right there. The red one would be standard deviation of x bar is equal to the standard deviation of the square root of 50. Now the question is which of these two will have a higher standard deviation of x bar? Well, note that these two will be the same exact value, right? Because whatever the standard deviation of my population is, that's what would go in for the standard deviation, or sigma right here. So since these are both the same, if I divided by square root of 15 compared to square root of 50, which would produce the smaller value? And as we look at this, we notice that the smaller value would actually be this one, okay, right here. So the second one, think about it, the higher the sample size, what happens? This produces a smaller standard deviation or a smaller spread. Same thing, right? So the more fish that I have, the smaller the standard deviation. Therefore, the one that would be more spread out would be the one with the least amount of the lower sample size, okay? So how do I say that? Well, we could say this a bunch of different ways. But we could probably say something to the side of, based on all this, the random sample for n equals 15 would have a higher standard deviation, making the data more spread out, okay? And that's just a statement, right? Well, think about it. If the data is more spread out, the question still becomes, when we look at 10 or something that is greater than 10, okay? So if I were to draw this picture, right, we don't know the standard deviation, but if this was 8, which is the mean, and I looked at 10, the data that is more spread out will have a higher shaded area, right? Think about it. If it's more spread out, then where you had 10 or greater would be highlighted more. But if this data is really, really tight, if it squeezes in, then the area that is shaded still is 10 or greater, but it would be a smaller segment. Maybe instead it would be something like this. So the higher probability would be the normal distribution that had more shade in it. Okay. I'm just seeing here. I would say I would just describe this. Okay. And I would just say exactly what I said, except a little bit formal. We could say something to the effect of, and just comparing them, since both samples have a mu of x bar equal to A, right? Or the mean of our sample equal to A. And, we'll just do this. We'll say this. The smaller sample size will have greater variability. Thus, the probability of x bar being greater than 10 will be shaded more for n equals 15 compared to n equals 50. Okay. Now you could have said a bunch of different things on that. You probably didn't have to do all of this. I just wanted to explain the background of this. The big new thing that you've got to remember is the larger sample size produces smaller variability, meaning that if we're trying to find 10 or greater, that means that if you have less variability, that means you're going to have a smaller probability of getting 10 or greater on the mean lengths of those fishes. So that's why you would put that there. Now let's look at the next thing. This next part is suppose the standard deviation of the sampling distribution of the sample mean for random samples of size 50 is 0.3. Okay, so it says suppose the standard deviation of the sampling distribution of the sample mean for random samples of size 50 is 0.3. If the mean length of the fish is 8 inches, use the normal distribution to compute the probability that a random sample of 50 fish will have a mean length of less than 7.5. So we know that because of, and we could maybe say this up here, and we could put the mean as 8. And it also says that the mean for random samples of size 50 is 0.3. So you don't even have to use this formula here. This is 0.3, right? It gave it to us. So we put 0.3 in. Excuse me. So what we've got now is 8 as our mean. We know that there. And what they're trying to do is say, okay, 7.5 or less. So we come here, we highlight this area. Okay, so we're trying to find the probability where x bar is less than 7.5. Okay, and that's what we're looking at there. That's the notation. Okay, now we might want to just put a statement of we say the sampling distribution is approximately normal since the population, okay, remember that? If we don't have to test the CLT or central limit theorem if the population is normal, okay, since the population is normal or approximately normal. All right, I'll put the approximately because it's probably good there, okay, because it does say approximately normal up here. Okay, so we've got that down. We've got this all established. The 10% condition, we don't even have to do because of the fact that it gave it to us. Okay, so we don't even have to worry about that. Now we just go straight into solving for the area that's here. Now I'm going to use a z-score, but just make sure if you use standard or if you do normal CDF, just be careful on that. Okay, so we're trying to find the probability where x bar is less than 7.5. And to do this, we say that it is equal to the probability, and this is where we put a little z-score in it. The z-score is less than my value, which is 7.5, minus my mean, which was 8, divided by my standard deviation, which was 0.3. Okay. Now we're just going to solve this to where probability of z being less than if we looked at it, it'd be like negative 1.67. Negative 1.67 there. And your value may be just a hair off, but we would say that this would be 0.0475. So we would say that the probability, and I would restate this, the probability that a random sample of 50 fish, and I'm just going to put interpret, but I'll say it to you just for sake of time. The probability that a random sample of 50 fish will have a mean length less than 7.5 inches is approximately 5%, or approximately 4.75%. Or you could say a proportion of 0.0475. Any of those options are good. Just be able to restate that and put that down there accordingly. Okay. Now the next one says, suppose the distribution of fish lengths in the lake was non-normal. So now it kind of counters what was said at the top here. The question is the same mean and standard deviation. So instead of putting n here, all we know is that mu is 8, which also, by the way, is mu of x bar, right? That's really what we're looking at. And we know the standard deviation of x bar is 0.3. By the way, do I have to know that the population or sampling distribution is normal in order to use these formulas? The answer is no, right? Remember we talked about on this side, we talked about that. Now, in order to use my normal distribution, normal CDF or z-score, I've got to show that the central limit theorem is true if the population is non-normal, okay? Now, the question is would it still be appropriate to use this? So the question is because we're talking about means, is my n greater than or equal to 30? That is the condition for the central limit theorem, CLT, for mean length, right? Now, if it was proportion, we would be talking about our n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Regardless, since we are now on our mean lengths, the question is my sample greater than or equal to 30? Well, in this first one, it actually wasn't, but it actually coming right back to the one that was on part B. I think it's this part B right there. And we know that 50 is greater than or equal to 30. So we could say that yes, based on the central limit theorem, for sample means, there it exists a sample size greater or equal to 30, making the sampling distribution, making sure now I'll probably put making the sampling distribution approximately normal. Here's what I'll read. I'll read theirs because theirs also is obviously theirs is the perfect, I don't want to say perfect answer, but really what they're looking for. Mine would still be okay, but here's what they say. Yes, the central limit theorem says that the sampling distribution of the sample mean will become approximately normal as the sample size increases. That's true, right? We didn't state that, but that is true. You might want to put that in there for context there. What is the central limit theorem? As the sample size increases, the sampling distribution becomes more normal, right? Now, then it continues and says, since the sample size is reasonably large, where n equals 50, the calculation in part B will provide a good approximation to the probability of interest, even though the population is non-normal. Yeah, I probably could put a little bit more information in there. I like their answer, obviously, but mine is still good to go. So that's what we would be looking for on this specific answer there. Okay? Awesome. If y'all have any other questions, I've got my phone and stuff out, and then I'm also on the group chat. I'll put your questions off to the side, and sorry, I can't type here. I meant here. My fault. My fault on that. So put those questions out there, and we will go through those together. As you go through these questions, I did want to just hit on a couple multiple choice. This is from the end of the chapter on chapter 7. This is for y'all. So any questions y'all have, interrupt me, whatever y'all need. and we'll go through those together, whether it's through Remind, email, or everything's coming straight to my phone. So just continue to help me with that, however I can help you there. Okay. All right, let's go through some multiple choice questions. These are, again, on the end of the chapter. If you want me to pull questions off of the Google form, I believe you're able to access that, so that might be a good practice for you. You could find that on the right side towards the top under the Chapter 7 topics page in On Campus. So just a heads up on that. All right, this one, 7-1, says, a study of voting chose 663 voters at a random picked them at random shortly after an election. Of these, 72% said they had voted in the election. Okay, so it's a study of 663. Election records show that only 56% of registered voters voted in the election. So this is off a sample, right? And this is off of population. That might be a good idea to just write those down, or just P or S. I think that'd be key. So really the 72% comes from the sample, which tells me it's a statistic because we think S and S. And a parameter is a value that comes from a population, P and P. So we asked the question, 72% is a sample and 56% is a population. That's incorrect. Even though it's related to a population, the population is all registered voters. The sample is 663, okay? So both of those are incorrect. 72 and 56% are both statistics. That's incorrect because we know that this is a parameter. C says 72% is a statistic, 56% is a parameter. It's actually the correct one, correct thing, because it is. 72% is a statistic, with the 663 being a sample, and the 56% is a parameter, with the population being all registered voters. Okay, so that's how we would figure that out for this one here. All right, 7.2 says Gallup poll, right? Talks about a Gallup poll here. The Gallup poll has decided to increase the sample of its random sample of voters from about 1,500 to about 4,000. Okay, right before an election. The poll is designed to estimate the proportion of voters who favor a new banning smoking in public buildings. The effect of this increase would do what? Well, going from 1,500 to 4,000 means we increase sample size, which, by the way, does what? Yes, you're right. It decreases variability. Nicely done. Okay, that's very important. So as we look at the sample size, as it increases, it does decrease the variability. So let's look and see what happens. Does it reduce the bias of the estimation? Well, we know that can't be true because it has to include decreasing variability. B says increase the bias of the estimate. Again, not true. C says to reduce the variability of the estimate. That looks pretty good. We're going to come back to that one though. D says it is increase the variability, which is incorrect. It decreases. And E says reduce the bias and variability of the estimate. Now, the question is whether it's C or whether it's E. Well, we remember that if we decrease the variability or increase the sample size, right? The bias, it all has to do with how I sample it, right? So if I took a sample of 50 basketball players, right? The first time, and let's say the second time it had 100, right? And let's say that when I took the 50 and I took the 100, I sampled incorrectly. Let's say I showed some bias, right? Let's say there was some non-response bias. Some people didn't respond. If that's the case, the fact that I increased the sample size would not decrease, it wouldn't affect the bias. Now, would it decrease my variability? Absolutely it would, right? This would be, this would lower my variability from 100 sample size to 50. However, it has no impact on the bias. So we say that it would only reduce the variability of the estimate, okay? Awesome. Let's go to the next one, 7.3. suppose we select an SRS of n equals 100 from a large population, having a proportion p hat of successes. Let p hat be the proportion of successes in the sample. For which value of p would it be safe to use the normal approximation to the sampling distribution? Well, we know that for this, n times p is greater than or equal to 10, and n times 1 minus p must be greater than or equal to 10. So if n is 100, right? So this is going to be 100. We would say for my first value, my first one would be 100p is greater than or equal to 10. For the second one, if I plugged in 100, because that's what was given, we know 100 times 1 minus p is greater than or equal to 10. So we're just going to basically solve this, dividing by 10 to where p is greater than or equal to 1/10 or 0.1. Okay. The next one we solve by doing 100 minus 100p is greater than or equal to 10. We subtract 100, and then we have a negative 100p. I'm just solving it here, equals negative 90. We divide by negative 100 to where p would be greater than or equal to 9/10 or 0.9. Okay. So what is that saying? That's saying that p has to be, and really when I divide by a negative, my fault, this should flip-flop, right? That's Algebra 101. So p's got to be between 0.1 but it's got to be less than or equal to 0.9. Okay, so what does it say? It says, for which of the value of p would it be safe to use the normal approximation? Okay, so as we look at this, we've got to say, okay, which of these values would make sense with what the question's asking? Which one would it be? Okay, so we look and see, okay, first off, this could be greater than or equal to 0.1, but that's right on the cusp of that normal approximation. So we're going to actually throw that one out, okay? 0.09, if I plugged in 0.09 in for this, oh, I'm sorry, hold up. 0.01 is less than 0.1, right? So because of that, we got to get rid of it. So is 0.9. 0.9 is same. 0.975 is greater on this, so we can't have that one, right? Because it says p's got to be less than or equal to 0.9. It actually is greater, so is 0.99. So the only one left based on solving using my CLT and based on saying, hey, which of these values are between 0.1 and 0.9, the answer would be 0.85, and that's how I would solve it there, okay? All right. Rock and roll. I'm hoping this is helping y'all. Let's go to the next one here. Number 4, 7.4, says the CLT is important in statistics because it allows us to use the normal distribution to find probabilities involving the sample mean. Okay. The question is what is the condition? Okay. What is the condition? So as I look at this, the question is all right, CLT is important because it allows us to use normal distributions to find probabilities involving the sample mean, okay? Now, sample mean, remember that this is n is greater than or equal to 30, right? So let's look and see. A says if the sample size is reasonably large for any population. We're going to come back to that one. That sounds pretty good, but we'll come back. B says if the population is normally distributed and the sample size is reasonably large. Well, remember, if the population is normally distributed, we don't have to use the CLT is not there, right? And by the way, if this is normally distributed for the population, we don't even have to use the sample size. Whatever the sample size is would be normally approximated. So we're going to cancel that out. CLT says it's important because it allows us to use the normal distribution to find probabilities involving the sample means. And we use the CLT. If the population is normal, we don't have to use CLT. We know the sample mean will be normal too, okay? So if the population is normal, then the sample is normal and we don't have to use CLT. D says if the population is normally distributed and the population standard deviation is unknown, that's false. And if the population size is reasonably large, that does not have any impact on my central limit theorem. So what does? The central limit theorem comes into play when the population is not normally distributed. It comes into play if the sample size, n equals whatever, is reasonably large. We say, well, what is reasonably large? That's where we bring in the n is greater than little n, sample size is greater than or equal to 30. That's a reasonably large sample size to use a normal approximation. Okay. I hate Ohio State, but hey, got to do what you got to do, and I'm wanting to help y'all out, so we'll do this one. Okay. Okay. So this one states the number of undergraduates at Johns Hopkins is approximately 2,000. Okay. While the number at the school, sorry, can't say it, is approximately 60,000. Both schools have an SRS of about 3% of the undergraduates that's taken. So the O has 60,000 in my population, and Johns Hopkins has 2,000. Each is taking a sample of 3% of my population. Okay, so this is my population here. This is my little n here, right? So it's 3% of, for this one's 2,000, okay? All right, the question is, each sample is used to estimate the proportion P of all students at the university who own an iPod, which would be like 0% now, but we'll just keep going. Suppose that, in fact, P probability is 0.8 at both schools, okay? So the P of is 0.8. So when we look at this, P, the actual proportion is 0.8. Which of the following is the best conclusion? All right. All right. So which has the which would have the larger sample size? Well, this will have the larger n, right? And this would have, we don't know what it would be. Well, we could solve that, but that would have the larger one. This would have the smaller n, right? So which would have more variability? Well, the larger the sample size, that means it would have less variability, okay? And this would have more variability, okay? Let's see if we could find that. It says this, the estimate from Johns Hopkins has less sampling variability than, yeah, it would have more variability, right? Not less, so we would cancel that out. That's gone, okay? The estimate from Johns Hopkins has more sampling variability than that from Ohio State. That's true, but we're going to come back to it. The two estimates have about the same. That's untrue because we saw that the sampling size is different. It is impossible to make any statement about sampling variability. That's incorrect. Because of the increased sample size, we say that B would actually be our answer for this one here, okay? So because of the fact that the sample size is greater for that other school, we say that it would have actually less variability than Johns Hopkins, okay? All right, let's go to the next one. Hopefully this is helping y'all. Okay, a researcher initially plans to take an SRS of size n from a population that has a mean of 80. So the mu population is 80. The standard deviation is 20. Notice I do not use mu of x bar or standard deviation of x bar because these two are talking about a population, okay? If he were to double his sample size to 2n, okay, so from n to 2n, the standard deviation of the sampling distribution of the sample mean would be multiplied by what, okay? First thing is let's find out what this would be normally. So we're going to take the standard deviation and divide it by the square root of square root of n, right? Square root of n. So if I were to solve this, this would be equal to 20 over the square root of square root of n, okay? So we've got that there. This would be my initial. But what if I multiplied n by 2, doubled the sampling samples that are here. Well, we would then have the standard deviation of X bar is equal to 20, that stays the same, over the square root of, now I'll just put 2n, right? And remember, this is the formula for the standard deviation of a sampling distribution. So what did I just do? Well, I just multiplied the bottom compared to this one by 1 over the square root of 2, right? It's really what I just did because I put 2n in for n. So really, what did I do? I multiplied it by 1 over square root of 2. We don't believe in rationalizing here in AP Stats, so B would be my correct answer, okay? Good. Hey, again, if you have any other questions, I haven't gotten any questions yet today. I see some viewers that are on there, but if you have any questions, throw those out there. Text me, email me, whatever you need to do. But unless you need some specific questions, I'm just going to continue to go through the end of chapter review on this, okay? All right, student newspaper. Large university asks an SRS of 250 graduates. Okay, so this is a large university, just a heads up. They ask, do you favor eliminating the carnival from the term end celebration? Oh, that'd be fun. We should have a carnival at GAC. That'd be good. All in all, 150 of the 250 are in favor. So this might be helpful. So like if it's 150 of 250, that means like P hat, because it's from my sample, of 150 over 250, which would be like 15 over 25, which would be like 0.6, right? 0.6 is P hat. Cool. So that's R in favor. Okay. All right. It then goes on to say, suppose that, unknown to you, 55% of all the undergraduates favor eliminating the carnival. So this is all, right? So P is 0.55. Cool. If you took a very large number of SRSs of size 250, right, we talked about that, from this population, the sampling distribution of the sample proportion P hat would be what? Well, anything that says exactly normal, guess what? You can eliminate. Because you know as well as I do, even if we showed CLT, we can't be exactly normal. There's no way. Okay, so the question is it approximately normal? We don't know, right? It doesn't say about anything about the population, what that shape was, and it really wouldn't matter because we're looking at proportions. So the question is n times P, is that greater than or equal to 10, or is n times 1 minus P greater than or equal to 10? And we'll check it out. So this would be 250 times P hat, right? Or times P is 0.55, my fault. Greater than or equal to 10 is 250 times 0.45. Greater than or equal to 10. I believe both would be, right? So they are approximately normal based on CLT, because both of these would be true. We can throw out the heavily skewed version there, okay? All right, the next question is what is the mean? Well, the mean of this sampling distribution, if we remember, it's n of mu of P hat, comma, the standard deviation of P hat. So as I look at this for number 7, the question is which would be correct? Which one would be correct here? Well, we know that the mu of P hat would be equal to, I think this is on your formula sheet, but it's equal to P, the actual P, which is 0.55, so we put that here. And the standard deviation we can solve for by doing the square root of P times 1 minus P all over the square root, all over n, okay? Now, we could actually solve for that, and that would be sufficient. But as we look up here with the mean of 0.55, both standard deviations would get 0.03. I think you would solve that here. So the correct one would be B, because the mean is not 0.60 when it comes to the sampling distribution. It is, however, for the sample that we took. Okay, so this is one sample distribution if we plotted all those, and then a sampling is the mu of P hat the mean of all samples that are there. Okay. All righty. We got a question here. Can we go over 2007 Form B, number 2, FRQ? I like it. All right, Jordan, if you could give me just a second, I'm going to pull that up here on my, I'm going to take a picture of it so I could show everybody what one we're talking about. Good, good. 2007. I'm going to make sure that one's the right one. 2007 Form B, number 2. 7. Okay, perfect. Okay. Let's pull that up. That's a good one. It's another one too that as we go through is a good one just to kind of know what to expect. You have a good idea of which FRQs are on the test because I showed y'all, told y'all there. So continue to push forward through that with those. We'll rock and roll. Let's see here. Is that, hopefully that shows up. Jordan, if that's not showing up, could you just shoot me a message there? But we'll go over this one. Okay. All right. It says the graph below shows the relative frequency. Notice it's not cumulative, right? Cumulative would be rising. It would always rise because as you go from 0 to 1, 2, it would be anything like the number of dogs and cats would be 4, anything less than 4. That's cumulative. Relative just means what is the proportion of households that have the number of dogs and cats or 0 dogs or cats, that would be 0.36 proportion, okay? But it says the total number of dogs and cats owned by per household, okay, per the households in a large suburban area. So the large suburban area kind of tells me that N is very large, okay? For instance, 14% of the households own 2 of these pets. Let me see here. I'm going to read this carefully again. Let's see how many, say how many is my sample size. I don't think so. Okay, I don't think so. We're going to come back to that if need be, but I think we're good. It says this, according to local law, each household in this area is prohibited from owning more than 3 of these pets. So this is like good, this is bad. This is breaking the laws, anything over here, okay? If a household in this area is selected at random, what is the probability that the selected household will be in violation of this law? Okay, so the violations, would it be anything that has 4, 5, 6, and 7, right? So the probability that the random household of X is greater than 3, right? Or you could say greater than or equal to 4. That would be sufficient, right? Because it is discrete, because it's either 0, like it's discrete because it's a specific value. It's not continuous. It's not a normal distribution. So we would say it's either 4 or 5 or 6 or 7, right? So how do we do that? Well, it'd be 0.07, notice, or, which means, we're adding there, right? And you can't have 4 and 5, right? We call those mutually exclusive, right? They're separate. I can't have a household that has 4 dogs and cats and 5, right? So you're either one or the other. So we add 0.04 plus 0.04 plus 0.02. So when I add all of those together, the probability of X being greater than 3 would be 0.17. 0.17 there. And probably interpret that would be good. 0.17 or 17% of the selected households or of the households will be in violation of this law. That's perfect. Okay. The next one says if 10 households in this area are selected at random, what is the probability that exactly 2 of them will be in violation of this law? Okay. So this is a little bit different because now we're going to move into I'm going to do this. I'm going to bring in my binom here. At this point, you either are in violation or you are not, right? That would make sense. So when you think about it, the number of households selected would be 10, right? And we're trying to see that what is the probability that X would be exactly 2 of these households. So the probability that that Y, in fact, I don't want to use X because I used that up here. It's a little different. Up here, this was like based on the chart, X is greater than 3. What are that? What's the probability that the more than 3 houses would be in violation, or that you would be in violation of the law by having 4 or more cats and dogs combined. Sorry, I'm getting this up here. So the question is what is the probability that out of 10, 2, exactly 2, would be in violation of this law? Okay. Well, to be in violation of the law, each time I select a house, the probability would be 0.17 to be in violation of the law, right? So the question is whether it's going to be binom CDF or binom PDF. Well, because it's Y equals 2, it's not cumulative, because cumulative would be like Y is greater than or equal to 2. So because of that, now we're going to go to binom PDF. So to establish context, we'll erase this here. We're going to put binom PDF, right? And in doing this, make sure. Perfect. Thank you, Jordan. Just making sure. Appreciate you putting that down there. Let me get this down. Perfect. Pull it up. Okay. You're going to go to vars, right? Or second vars, my fault. The distribution. And you're going to go down to binom PDF because we're just looking for 1. The trials that we have is 10, right? The probability would be 0.17 because we solved it in the previous one. 0.17 per random household we have. And X is 2. So exactly 2 of the 10 households that are there. Okay. So we're going to press enter. And so to write this, we would actually put binom. We'd put trials, comma, probability. You could put N for trials, that's fine. Comma, probability, comma, my X value, right? Which, what did they say on that last one? They said, I know 2, I think it said X value. No, that'd be sufficient. All right, we established context. Now we go to binom PDF. The trials is 10, probability is 0.17 from A, and the X value is 2. Okay, so once I plug that in, press enter, and I get a probability of 0.293, right? So this is 0.293. So context-wise, what we say that if 10 households in the area is selected at random, the probability that exactly 2 of them will be in violation of the law will be 0.293 or 29.3%. Okay? All right, the next one. The mean and standard deviation of X are 1.65 and 1.851. Okay? So what is X? X refers to my population. Okay? So in writing this, we would say mu is 1.65 and my standard deviation is 1.851. Suppose that 150 households in this area to be selected at random. Oh, there it goes. Okay, there it goes right there. 150, which would be my N. The mean number of dogs and cats to be selected at random, and the mean number of dogs and cats per household is it to be, suppose that in this area are to be selected at random and at X. The mean number of dogs and cats per household is to be computed. Describe the sampling distribution of X bar, including its shape, is it normal or not, center, what is the mu of X bar, and spread. How's my variability? How's my standard deviation? Okay, so in drawing this, we're trying to see a continuous graph. Can I approximate it as normal? We can't yet until we show, based upon the mean lengths, right? We're talking about mean here, all right? Is the mu of X bar, that relates to center, that's what we're going to find there, right? Is my standard deviation of X bar. This talks about my spread, when I find that there. And my shape goes to my CLT, my central limit there. So let's do that real quick. This may be all around here, but hopefully this will help you. I could do, let's do this, the normal distribution. So CLT is N greater than or equal to 30? And yes, it is, because we've got 150 households. So based upon my shape, I would say that based on the large sample size, we can conclude, based on the CLT, central limit theorem, that the sampling distribution will be approximately normal. Okay? I'll read you theirs just so you see it. This was from my interpretation. They said it will be approximately normal, or is more symmetric than the population distribution, which is highly skewed. I'll take either. You'll notice that this is skewed, right? Based upon the data that's here, it's actually skewed right. Okay, so just a heads up there. You could mention that in there, but did not have to. So we've got our shape. Our center, which is mu of x bar, is equal to the actual mu. So this mean would actually be 1.65, okay? So we would say the average household within the community would have approximately 1.65 dogs and cats combined within that, okay? They didn't even put context there, but I always like to just in case, okay? For my standard deviation, this would be standard deviation over the square root of n, which would be 1.851 over the square root of 150. And when plugging that in, I get 0.1511. Okay, so this right here would be, if I were to interpret it, the spread of my data, or you could say the average distance each household would be away from my mean of 1.65. Any of those would be good in interpreting it. They didn't even, they said to describe it, but they actually would give you full credit if you just put the numbers down. I like to put context because you just never know what they're expecting there. But that's how you would do that one. Jordan, I hope that helped there. If you have any questions, let me know, okay? All right, anybody else have any other questions? Checking my phone, checking different things. And just like that, we are 57 minutes into the podcast. Aren't you pumped up? Hopefully this is helpful for you, whether you are watching this live or whether you're watching it tonight, later on. I understand it's a weird time, but tonight got some stuff going on with my girls there. So that's why we're doing it. 7.9 and 7.10, we may finish up with these two unless there's another question, all right? 7.9, machine is designed to fill a 16-ounce bottle of shampoo. When the machine is working properly, the amount poured into the bottles follows a normal distribution with a mean of 16.05 and a standard deviation of 0.1. So mu is 16.05 and my standard deviation is 0.1, okay? Awesome. So we've got these two, okay? Got these two. As we look at that, it says assume that the machine is working properly, okay? If 4 bottles are randomly selected, so n equals 4, and the number of ounces in each bottle is measured, then there's about a 95% chance that the sampling mean will fall which of the following intervals. Ooh, this is really good. Because of the fact that we're talking about mean here, if n is 4, the sample mean, right? We're talking about sample mean, would be this. Well, it's approximately normal. So we're going to say n is mu of x bar, comma, standard deviation of x bar, right? Well, the mu of x bar, sorry, not equals, mu of x bar is equal to mu, which is equal to 16.05, okay? So we're going to put that there. And the standard deviation for this would be the standard deviation of x bar is equal to the standard deviation over the square root of n, or 0.1 over the square root of 4, okay? Well, if I keep going, 0.1 divided by 2 would be, make sure, is that 0.25? No, 0.05? 0.05. Yes, okay. 0.05 would be my would be my standard deviation. So the question is if I were to normally approximate this with a mean of 16.05 and a standard deviation of 0.05, this brings it back here. What about the 95%? Well, we remember that one standard deviation to the left and right is 68%, right? And two standard deviations to the left and right is 95%. So if I can add two standard deviations to the left of 16.5 and to the left, right and left, we can add 0.05 twice. So 0.05 times, or plus 0.05, 16.05, sorry, and plus 0.05 again. This would be 16.10 and 16.15. If I subtracted it, it would be 16. And if I subtracted it again, it'd be 15.95. So the two values would be 15.95 and 16.15. That's how I got C. Okay? It's a good question. That's a really good one. All right. And again, we didn't have to show CLT because it also said that it follows a normal distribution for the machine or the population. Last one, 7.10. Suppose that you are a student, aide in the library, and agree to be paid according to the random pay system, which would be very entertaining, by the way. That'd be so awesome. Like, I could win $1 million. I could get paid $1 million this year or $1,000. Like, there'd be a lot of excitement there. That'd be kind of cool. Each week, the librarian flips a coin. If the coin comes up as heads, your pay for the week is $80. If it comes up as tails, your pay for the week is $40. You work for the library for 100 weeks. Suppose we choose an SRS of 2 weeks, okay? So here we go, 2 weeks. We have our population. We'll use big N because we know what that means. Big N is 100 weeks. Okay. Calculate your average earnings of X bar. The shape of the sampling distribution of X bar will be what? Okay. Suppose we choose an SRS of 2 weeks and calculate your average earnings of X bar. Okay. Wow. Okay. Well, it doesn't say anything about the population. So it's weird because it kind of takes you on this loop, and then it kind of throws this question in here that I'm like, we kind of needed to know parts of this. We really maybe didn't, depending. Well, let's look and see. Let's see what we got here. It says this: suppose that you are a student aide in the library, agree to be paid according to the random pay system. Each week, the library flips a coin. If the coin comes up as heads, your pay for the week is $80. If it comes up as tails, your pay for the week is $40. You work for the library for 100 weeks. Population. Okay. Suppose we choose an SRS of 2 weeks. How would you calculate your earnings for X bar? Well, I'll be honest, this one's not an easy one. And the reason why is because as we look at this, you kind of can see that if I were to write this out right here, right? The fact that it's 50-50, right? The probability is 50-50 with this. We're really not looking for the proportion, though. We're looking for X bar. So the mean amount that I would get, because the probability is the same, if I were to conduct a, like let's say just a bar graph right here, and I said, and if I did this for 100 weeks, and I got either $40 or $80, right? I could expect that out of this 100 weeks, let's say 100 weeks is up here, I could expect that on average about 50 of those I'll get $40, right? And 50 of them will be 80. So this is going to be symmetric, is it not? It's going to be symmetric. But as we look at this, the N has to be greater than or equal to 30 in order for this to be approximately normal. Doesn't say anything about my population. So because of that, I can't assume, because there's only 2 weeks that are taken, I can't assume that it's normal or even approximately normal, okay? Now the question is it right skewed or left skewed? Well, because of the fact that we're taking this and we don't know what the population is doing, We don't even know what the sample's doing. We can eliminate the right and left skewed, which leaves us with a symmetric graph. As you can see here, this is symmetric, right? Except when it's symmetric, it won't be normal. So I can expect them to be the same, symmetric, equal, but they're not normal. And so that's what you would expect out of 7.10. It's a little tougher. That one was a little bit tougher there. Okay. Hey, I hope this was helpful for you. Care about y'all so very much. And man, I want y'all to be successful on this test coming up. My big thing is if you have extra questions tomorrow at 7, I will be available for you. Come in with questions, ask around, whatever can be done to get you ready for that test. The only other thing I got to do is my traditional shot. Here we go. That was awful. Let's do it again. Sorry. I got to do it. Here we go. Ready? 3, 2, 1. That looks good. Oh. Hey, have a fantastic day. And see you, team. Bye.